Hi everyone, welcome back to Math 256. This is Scott. Let's get started. So now we're going to be talking about section 2.2, in which we will be discussing equilibrium solutions and stability. So here is the setup. We will be talking about autonomous first-order differential equations. So an autonomous first-order ordinary differential equation. So in other words, the form is going to be dx dt, so now notice x is the output, t is the input, is just going to equal some function of x. So no t. No t involved. That's what makes it autonomous. So these are what all of the population models that we were talking about before all fell under. So this heading. Now here's the idea. Even without solving an autonomous diffeq, we can determine a lot about the behavior of solutions. So in particular, just look at the format of the differential equation that we were discussing here. Dx dt equals some function of x. So since there is no dependence of t over here, it's all going to depend on what the current value of the x variable is. So what that means is that we will be able to know everything there is to know about what's going to happen to a differential equation solution if we know what its current value is. Now then, we can look at critical points, which are what happens when this equals 0. So critical points, these are our values for which dx dt equals 0. These give constant solutions. So these give constant solutions or equilibrium solutions. Now a phase diagram is a display that shows you the equilibrium solutions as well as the behavior of solution curves near those equilibrium solutions. And as an example, so here's basically the way this the way this would be laid out. So an example for how this looks. It looks like this. So phase diagrams, they can be oriented either horizontally or vertically. I think that it's a little bit more intuitive to do it vertically. The main reason typically why they're done horizontally, I think, is actually to save space in typesetting and such, like in books. But you could say something like this, where you have a value, let's say 0, you have a value of 10. So these would be the equilibrium solutions. In other words, the constant values of 10 and 0. And then you would just indicate when it's below 0, which direction is it going? Is it going up towards 0, or is it going down away from 0? And it might be doing something like this, and then like this. And same thing at 10. So you would just give an indication of solutions that when they are below 0, are they going towards 0 or away from 0? When they're between 0 and 10, are they going towards the 0 or are they going towards the 10? And when they're above 10, are they going towards the 10 or away from it? And then we can use this to sketch rough solution curves. And the way that would look is you would put dotted lines for each of the solution for each of the equilibrium solutions, and then this would be, this is the x-axis here, this is going to be the t-axis. And then based on this indication, anything that starts off below 0 is going to tend upwards towards it. Anything that starts above 0 is going to tend upwards towards the 10. And anything that starts above the 10 is going to come down and approach it from above. So we can at least sketch that degree of it. We don't know how fast it's growing, how fast it's shrinking, how fast it's approaching these things, but we can at least tell what their tendency is going to be. Now here's how we make these. How to make these. So what we just need to look at is in our differential equation, which again has the form dx dt just equals some function of just the x, we can just graph y equals f of x, and let's say it's going something like this. So we can just make a graph of something along these lines, for example. And then everywhere where this graph crosses the x-axis, these are going to be equilibrium solutions. So everywhere where the graph crosses the x-axis is going to be an equilibrium solution, and so here, so the crossings, so the places where f of x equals 0 will be equilibrium solutions. And then the places where f of x is positive will be where the solution curves go up, and the places where f of x is negative those will be where solution curves go down. So here we're talking about minus, we're talking about plus, and we're talking about minus. So this whole phase, so the phase portrait here would be this value will go with that one, and below that value it's going to be going down because it's negative. Between them is going to be going up, and then above it is going to be going down. Now an example more specifically here would be something like one from our catalog of examples of ODEs. We could do Newton's law of cooling. Where we could have dx dt is equal to k times a minus x. So this would be one way of formatting it. So in other words, the ambient temperature minus whatever the current temperature is times a positive coefficient. Now, if we were to graph this, then what we would be getting is something that crosses linear, and it goes down like that, and it will be positive on this side and negative on this side. So what that's going to mean is that the phase diagram here is going to be A, and when the x is below A, it's going to be going down. When x is, sorry, it's going to be going up, I should say. And when x is past A, it's going to be going down. So then what that means is all curves are going to be going like so, where this is A. So we've got everything below pointing upward, everything after pointing downward. So sometimes these are also laid out like so. Oops. Shouldn't really put arrows on them. I should just draw it like this, and then A going up like that, and down like that. So sometimes they're laid out that way too. All right, now now stability. Stability refers to the behavior of a particular phase diagram near a certain solution, near a certain equilibrium solution. So we can have three categories basically. There are what are called stable solutions or stable equilibria. And these are where both arrows point toward the equilibrium. These are also called sinks or attractors. So sinks, like where a drain goes. Or attractors. If you ever heard the expression from chaos theory, strange attractor, that refers to this sense of the word. Then we have unstable solutions. And this is where both arrows point away from the equilibrium. And that is also called a source. So also called sources or repellers. And then we have what we, in this section anyway, are going to call semi-stable. Solutions. And this is one arrow points towards one arrow points away from the equilibrium. So these are sometimes also referred to as stable in one direction. Now the way these can look is, so the way these can come about is if we had something like this. So here, another way these are often labeled is x prime and x. And then what we'll have on it right here is positive, positive, and then negative, and then positive. We've got three equilibrium solutions, a high one, a middle one, and a low one. And we've got positive, positive, then we've got negative, then we've got positive. So let's say this is A, B, and C. A, B, and C. So here, this one is unstable because both arrows are pointing away. Here, this one is called stable because both arrows are pointing in. And here we've got semi-stable because one is pointing towards, one is pointing away. And the way the solution curves for a differential equation who had these as its three equilibria would be anything below A would veer up towards it, anything above A would go up towards B, anything above B would go down towards it, and then everything above C would continue up away from C. So the reason why these are called what they're called, and the reason why they're worth studying, is that they tell you basically the behavior of those specific values. Is it something that the function is tending towards, such that if it were slightly off, it would nonetheless converge towards it? Or is it something that if it gets even slightly perturbed away from that value, it will spiral away in a faster and faster way? So now let's look at some of the ones that we've just been examining under these cases. So special examples. Let's take the logistic. Let's take the logistic model for one. So dp dt is equal to 0.05, actually, yeah, we'll just take as a specific example, 0.05 p times 100 minus p. So these are both, of course, open for debate. Now, thinking about this just as the quadratic that it is, so it's p squared, negative 0.05 p squared minus, plus, and then here it's going to be 5p. So this is a quadratic. It's going to be facing downward, and it's going to have roots at 0 and 100. So it's going to be a parabola like that. This is going to be p prime and p. And here it's plus, here it's minus, here it's minus. We don't often think of populations as going negative, but the equation doesn't know that. So then, at 0 and at 100, we've got the following. So 0 going down from there, above from there, and then below from above there. And so that makes this one stable, and this one unstable. And that would give us as characteristic solution curves the following. So if it was above 100, it would tend down towards it. If it was between 0 and 100, it would be on a usual, what we think of as kind of the typical logistic path. Then if it's below 0, it'll be an exponential growth downward. Now that doesn't happen so often in actual physical populations. However, we could be talking about something like money or something like that, where negative values do have, unfortunately, all too true a meaning. So what this means is any population that's anywhere even close to 100 will converge towards it. Any population, though, that's even slightly off from 0 will diverge away from it. Now, let's look instead at the explosion versus extinction model, which has a very similar equation, but with a slight twist. So explosion versus extinction, now dp dt could be something like 0.05 p times p minus 100. So it's basically just the exact opposite of the one that we just saw, which means that the parabola, instead of having the positive orientation, is now going to have the negative, or sorry, instead of having the negative orientation, it's now going to have the positive orientation, you could say. So it's going to be minus, plus, and plus, which means that although it has the same two equilibria, 0 and 100, the behavior is opposite, which now marks this as unstable and this one as stable. So what that means now is we're going to have populations that, if they were negative, are going to veer up towards 0. Again, doesn't quite make sense in the context of animal populations, but there could be other scenarios that use the same sort of equation. Now here, if we start anywhere above 0, it's going to verge down towards 0. That's the extinction side of things. And if we start anywhere above 100, then it starts growing exponentially from there. And that's why it's called explosion on the one hand versus extinction on the other. There is a certain threshold. Above it, your population will explode. Below it, your population won't even sustain itself. There is no stable outcome here other than extinction. And then one last twist here, which is called harvesting. So this is where you have a logistic growth model, but there is a certain other factor in play that harvests out some of the population. So we have maybe say dp dt is equal to something like 0.05 p times, and now here I'm just going to write it with m and p minus h. So this is the coefficient of harvesting. So now what happens is we take the same classic parabola that we had from before, but now what's going to happen is that the whole thing is going to be shifted down by the minus h. And now we no longer have an equilibrium at 0, and we no longer have an equilibrium at the same value of 100 as we had before. The new equilibria are going to be changed, and they're going to be changed based on this. So the parabola is shifted downward, is shifted down h units, and this changes the equilibria. So now we have two new equilibria, A, which is slightly off from 0, and B, which is slightly off from n. And if h is large enough, so if h is large enough, the whole parabola can be shifted below the axis, and no more equilibria would exist. To learn more, this is going to be actually the subject of a project coming up. But right now, that's all I want to say about that. And so, until next time, bye.